Hello, pre-calculus students. This is Miss Robinson, and today I will be finishing up those 4.1 vocab notes with you. Okay, so if you start at vocab number 8, we have turning points. Turning points are points on the graph of a function when the function changes from increasing to decreasing or vice versa, decreasing to increasing. Okay, so let's consider the situation where we are increasing. So we are increasing here. Our graph is going up. Our y values are getting larger as our x values are getting larger. And then we change. We turn down and we start to decrease. We're decreasing. That point where we change from increasing to decreasing would be called a turning point. Okay. And again, if we are decreasing, our y's are getting smaller as our x's are getting larger, and then we suddenly change and begin increasing here. That point where we change directions is another instance of a turning point. Okay. So anytime that our graph changes direction, increasing to decreasing, decreasing to increasing, we would call that a turning point on our graph. Okay. All right, so we have a few rules for these turning points. Okay. So if a function f has a degree n, so that largest power of our function or polynomial, then that function f has at most n minus 1 turning points. In other words, or aka, if the graph has n minus 1 turning points, then f has at least n degree. Okay, so we can never have more turning points than we have degree. We must always have at least one less turning points than we have a degree. If we test that out with a function that we know very well, say the x cubed function, we can see the parent function of x cubed. If we graph that, looks like this. We actually don't have any turning points for this function because we are increasing to increasing, so we have 0, which is definitely less than cubed. Okay. Maybe if we add more zeros to this, so we have f of x equals x minus 1 times x plus 1 times x minus 3 maybe. That gives us still a degree of 3. 1, 2, 3. But this time we have a 0 at -1, +1, and +3. So we should have something that looks like this. Okay. And that's obviously the maximum zeros that we can have for this function, correct? We couldn't have any more zeros than 3 if we have a cubed function. If we look here, we only have, again, 2 turning points, which is 1 less than our degree 3 for n. Okay, so those are the rules for turning points of a polynomial function. Okay, now let's start discussing end behavior. Right. So end behavior means literally the behavior as your graph nears the end. Now we know that all of these polynomial functions are continuous, so they go on forever, but as they near our end, as they approach that infinity or that negative infinity, there's some special unique qualities for polynomial functions. So we can say that as x grows large, either positively or negatively, We can also say this as x approaches positive infinity or x approaches negative infinity. Then, any polynomial function of degree n, so remember that sort of function should be in the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus as many terms as is necessary plus a sub 1 x plus a sub 0. So remember, that's our form for a polynomial function. So any polynomial function of this degree n resembles the power function of the same degree. Okay, and of course this would resemble f of x equals a sub n x to the nth. So that same degree n, except without all of those terms. It's just the monomial part of that polynomial function. And let's test this out. Okay, so if we grab our graphing calculators here and turn them on first, and we look at our functions, let's clear out what we have already. Let's take a function that we already know, so maybe x to the third. So let's do 2x to the third power plus maybe 5x minus 10. Okay. Let's think about what this definition that we just came up with implies. So this n behavior should resemble that same function, except only the monomial term. Okay, so those two functions should resemble one another. So if we graph those, let's first look at our window. Negative 10 to 10 will give me some fairly large values. So that's a good x window to have. Let's zoom fit this and graph it. Okay, so we graph these two functions. There's my first function, the polynomial function, and there's that power function that it should resemble. And if you see right now, since my window is so large, 10 to the third power is quite a large number, I can see that these functions are lying almost directly on top of one another. So these functions are very close to one another when I take values where the y's tend to be very large. If I were to zoom in, I might see some differences between these two functions. In fact, I should see some differences. But right now, with these larger values, I see that the functions are very similar here. Okay. So that is essentially the idea behind n behavior. Okay. That is it for the vocab for this section. Your next video to be watching is example 1, so make sure that you also go to view example 1 for this assignment.